In the early 1970s, NASA needed a new reason to exist after the moon landings. Money tightened and politics shifted. So the agency sold a bold promise, a space shuttle that flew again and again like an airplane, making spaceflight routine and affordable. That promise bought support, but it also set a trap. The shuttle had to look cheap on paper, even if that meant gambling later. To fit shrinking budgets, the design bent toward what could be built and approved quickly. The shuttle relied on a large external tank to feed its main engines because carrying all that fuel inside the orbiter would have made it too heavy and expensive. That tank needed insulation so it did not ice over and shed chunks during launch. NASA used sprayed-on foam. It saved weight. It also introduced a new kind of debris. Here was the hidden trade. The orbiter rode beside the tank, not on top of it. That put the wings and heat shield directly in the line of fire if anything came off. Every pound saved on the tank mattered, and every new protective layer cost money and time. Under pressure, the program accepted vulnerability as a design feature. Foam shedding did not look like a disaster yet. It looked like an inconvenience. By the late 1970s, the shuttle's external tank and its heat protection system moved from drawings into hard testing. The tank had a simple job with high stakes: carry propellants, then fall away. To do that, it needed thick insulating foam, sprayed on to prevent ice and protect the tank's metal from extreme cold. But as engineers tested how it behaved under vibration and aerodynamic force, they saw a problem early. Small pieces of foam sometimes came loose during ascent. At first, foam loss looked like a messy nuisance, not a deadly one. The shuttle climbed through the atmosphere at enormous speed, and anything that fell away became debris, moving like a projectile. Engineers tracked where foam separated and how big the pieces were, and they compared that to the orbiter's fragile thermal protection tiles. The assumption held that the foam was light enough and the tiles tough enough that damage stayed within a repairable range after landing. That belief slowly hardened into routine. Each test and review turned foam shedding into something to watch, document, and fix later, not something that stopped the program. The damage was treated like maintenance, an item for refurbishment between flights, because the system was built around flying again and again. Warnings did not disappear, but they lost urgency. A known hazard became familiar, and familiarity made it feel controllable. The risk stayed in the design, and it stayed in the culture. In April 1981, the shuttle finally flew. It launched like a rocket, then came home like an airplane, and that alone felt like proof that the gamble worked. But the first flights also delivered a quieter message. During ascent, bits of debris struck the underside of the orbiter. When the vehicle rolled to a stop back on Earth, the inspection teams found damage on the heat shield tiles, small chips, missing corners, scars that had not been predicted on paper. Those tiles mattered because they acted like a skin that kept re-entry heat out of the structure. They were light, and they were fragile, and there were thousands of them. A strike did not have to be huge to leave a mark. Engineers mapped the hits, counted broken tiles, and replaced what they could before the next flight. The key point was the outcome. The shuttle still returned safely, so the damage got filed under something manageable, not something that stopped the program. That early success created a powerful pattern. Each time a mission ended with a safe landing, the story became that the system could take a beating. Debris hits turned into another item on a post-flight checklist, not a reason to pause and rethink the design. Repairs became part of the routine, and routine felt like control. But the evidence remained there in the tiles, real strikes in real flight, showing that impacts were not rare accidents, they were built into the way the shuttle flew. After Challenger, NASA slowed down and rewrote the rules. The shuttle stopped being treated like a routine service and started being treated like a high-risk test program again. Reviews became tougher. Paperwork grew heavier. People swore the culture changed. But the shuttle still sat at the center of big promises. Science missions, military needs, national prestige, and the pressure to fly did not disappear. It only changed its shape. The return to flight effort fixed obvious weaknesses and demanded stronger proof before accepting risk. Yet, day by day, the same old problem returned. The program had to meet dates. Managers had to balance safety with a schedule that kept slipping. Over time, attention shifted from eliminating every known problem to controlling it. If an issue appeared, the first question often became whether it matched something seen before. That logic sounded responsible, even cautious. If a shuttle landed safely after an anomaly, it felt like evidence. The anomaly became data, then history, then precedent. A known problem turned into a managed problem. Engineers tracked limits, wrote reports, and built workarounds. Each success made the next concern easier to absorb. The safety culture existed, but it started to orbit the schedule, not the other way around. Through the 1990s, the shuttle kept flying, and the external tank kept shedding foam. Pieces broke loose during ascent and struck the orbiter, sometimes leaving chipped tiles and gouges that got photographed and logged after landing. Each time, engineers compared the damage to earlier flights and asked the same question: was this getting worse, or just more of the same? The records grew, so did the arguments. One area drew special attention: the bipod ramp, a foam-covered shape near the front of the external tank where it connected to the orbiter. Investigators traced multiple debris events back to that spot, and the pattern felt uncomfortably consistent. Engineers proposed changes. Different foam application, reshaped contours, added testing, but every fix competed with cost, schedule, and the fear of creating new problems. The debate stayed open because nothing had yet forced it closed. Flight after flight returned safely, and that outcome carried enormous weight. When the orbiter landed, the damage became a maintenance task instead of a mission failure, and the urgency faded. Warnings turned into trend charts. Concerns became paperwork. Proposed fixes got delayed, narrowed, or treated as optional upgrades because the program's lived experience suggested the system could take the hits. Success, repeated often enough, acted like proof that the risk stayed acceptable. In January 2003, Space Shuttle Columbia lifted off on mission STS-107. A science flight that was supposed to be routine in the way the shuttle program had learned to expect. But less than 2 minutes after launch, the familiar problem returned in an unfamiliar way. Insulating foam broke free from the external tank. It did not just tumble away. A large piece hit Columbia's left wing at high speed. The impact mattered immediately, even if no alarm sounded. Foam strikes had happened before, and that history shaped how this moment got understood. Earlier hits had usually meant scuffed tiles, dents, and paperwork after landing. This one was different in scale and in where it landed. The left wing's leading edge took the blow, the area that faced the hottest air during re-entry and protected the structure behind it. Size and location changed everything. A strike that might have been repairable on the ground now carried consequences that only appeared later. What made the situation so dangerous was that ascent gave no clear way to measure the damage. The shuttle kept climbing, the mission continued, and the crew shifted to the work they had trained for. Meanwhile, the key fact stayed locked in those first seconds. Something hit the wing harder than the program's past experience had prepared it to accept. It was not just another chipped tile scenario. It was a new damage case created in flight with no easy proof of how serious it was. In the first days after launch, attention shifted from the dramatic moment of the foam strike to a calmer routine in orbit. But some engineers did not let it go. They knew the impact looked different, and they also knew one hard fact: nobody on the ground could truly see the left wing anymore. So they pushed for outside help, high-resolution images from military assets or government satellites to find out what exactly had been hit. The request sounded simple: get sharp pictures, confirm damage or rule it out, then plan accordingly. Yet the response inside the program did not match the urgency. Managers treated the strike as another familiar problem, something the shuttle had endured before. The idea of calling in military imaging became framed as unnecessary and complicated. The risk was not denied outright. It was quietly pushed into the category of non-critical. That decision carried weight because it shaped everything that followed. Without clear images, the team stayed trapped in guesses, not measurements. Engineers kept trying to raise the issue, but the system rewarded reassurance over escalation. The foam hit became a talking point that ended with a shrug instead of a plan. In orbit, Columbia kept operating normally. On the ground, a chance to learn the truth early slipped away. As days passed in orbit, the foam strike stopped being a single dramatic moment and became a technical problem that refused to go away. Engineers kept running the numbers with the limited data they had. They compared impact estimates to known materials, asking one hard question: could something have cracked the wing's reinforced carbon-carbon leading edge, the heat-resistant skin that took the worst of re-entry? The answer never landed cleanly, and that uncertainty mattered. Some models suggested tile damage would have been manageable, but a breach in the leading edge changed everything. If hot gases got inside the wing during re-entry, the structure could fail from within, quickly and without warning. Analysts worked through scenarios that ranged from minor harm to a hole large enough to be fatal. But without high-resolution imaging, they could not confirm any of it. The risk lived in estimates, not in proof. That uncertainty stayed largely trapped inside briefings and technical discussions, softened by careful language and competing interpretations. The crew received information, but not the full weight of the worst case. No one stood in front of them and treated the leading edge as a possible life-or-death breach that demanded a different plan. The mission continued on its timeline, with the most dangerous possibility hanging in the background, unresolved and unspoken at full volume. On February the 1st, 2003, Columbia began its return to Earth, as it had many times before. At first, the plan held. Then the damaged left wing met the real test that orbit had delayed. As the shuttle hit the upper atmosphere, air in front of it heated into plasma, hot enough to melt metal. That heat found a path inside the wing where it never belonged. Sensors began to show trouble on the left side first. Temperatures rose in places that stayed cooler on normal entries. Then pressure and structural loads shifted as the wing weakened from the inside out. The vehicle started to lose control authority, forcing its guidance system to work harder just to stay on course. Within minutes, the wing's internal structure failed, and the shuttle broke apart at high speed. The investigation that followed did not stop at the foam strike. It traced how the danger moved through the system without being treated like an emergency. Repeated past successes had trained the program to see foam loss as routine, not as a warning, and information did not travel cleanly between working engineers and decision-makers. Concerns were filtered, requests were softened, and uncertainty became permission to do nothing until re-entry made the decision final. Columbia's loss forced NASA to treat what had once been tolerated as a warning system that had failed. The idea that debris hits were simply part of flying ended. Oversight changed and engineering concerns no longer fit into a narrow box labelled acceptable history. Safety and mission success stopped competing on paper. They became linked in governance, with clearer authority to challenge assumptions before a launch ever happened. The most visible change landed on the external tank. Foam shedding no longer counted as a nuisance that technicians cleaned up later. It became a redesign problem with deadlines. NASA reworked the areas that had produced dangerous break-offs, including the ramp shapes and application methods that had proved unreliable. Each adjustment aimed at one outcome: fewer surprises during ascent and fewer chances for a strike to turn into an unrecoverable breach. But redesign alone did not answer the biggest question: what happened if damage still occurred? So the shuttle era gained something it lacked at the start: ways to look and respond. On-orbit inspection became expected, not optional, and repair concepts moved from theory toward capability. The program shifted from hoping a hit was survivable to proving the vehicle was safe because the cost of guessing had already been paid.